Hey guys, so we wrapped up rotational dynamics. Now we're going to go and we're just going to real quickly go over rotational equilibrium. There's not much to it. I'm going to do this video, which just goes over a few of the fundamentals, and then I'll do another video that has example problems. And so first, to talk about equilibrium, let's go back to what it means for linear. So if you recall, for linear motion, if I have an object which is sitting still with a zero velocity, then we would refer to that as static equilibrium. I can also have an object that's in motion with a constant velocity, which we would refer to as dynamic equilibrium. In both of these cases, though, what it means is that the acceleration is zero. And if the acceleration is zero, then we know by Newton's second that the net force acting on the object is also zero. So this is the condition for linear equilibrium. And in fact, it works, this is for 1D, but it's 2D as well, because we can split this up. And we would say all of the net force in the x direction equals zero, and the net force in the y direction is also equal to zero. So this is actually going to be our first condition for rotational equilibrium. So let's go to an object which can rotate. So we have a plank, which is this nail or bolt is kind of holding it against in the wall. This is a wall. And then you have a rope kind of hanging it up. So it's going to be an equilibrium, but what we're going to want to do is think about everything, what makes it be an equilibrium. Well, firstly, it's not moving in the x or y direction. So we know that the net force in all directions really is equal to zero. That's our first condition for equilibrium. The net force is equal to zero. However, this thing can also rotate. So that's what's important. So it could, if we took out this pin, this thing would probably rotate in this direction. And if we cut the rope, it would clearly rotate in this direction. So there's some rotation that could happen, but it's not. And it's not happening, and that's because the net torque on this thing is zero. So the net torque is also equal to zero. So these are our two conditions for rotational static equilibrium. Net force is zero, net torque is zero. And it's in these torques that you're gonna have to figure stuff out. So clearly we have, if we think about the forces involved, because remember torque is gonna be our force times distance. If we measure distance, say from, well, it doesn't matter. Let's just think about the forces. We see that we have a force here. That's the force of the, say, bolt. And then we're going to have a force at an angle here. That would be tension. However, these are not going to cancel out because there's another force that's acting on this, and that has to do with the actual mass of this plank, which acts at the center of mass. And so right here we have another one, which is pulling down on it. And this would be the force of gravity. So this is the one that typically gets overlooked, is this force of gravity, because it may not be as apparent. But you got to remember things have mass. So this force right here is actually trying to torque it this way. And then this is also trying to torque it in the same direction, and then tension is counteracting that. So make sure that you don't forget about center of gravity. Speaking of center of gravity, what does that mean? So we need to go back and think about center of mass. So center of mass, if you recall, you have this equation, to find the center of mass for different objects in a system. We just take the mass times their displacement from some position, multiply them up and add them, and divide by the total mass of the system. That will tell us where the center of mass is. For instance, in this case, we have mass M and 2m connected by a light rod, so no mass. If we wanted to find the center of mass for this thing, we would just add up. So x center of mass would be mass, and you can put your zero wherever you want for this. So I'm going to call this x is 0 here, and then over here x equals L. So in this case I would get mass times 0 plus 2m times L divided by the total mass, so 2m plus m. So I would get 3m. So you can see up on top that's 0, so I get 2/3. The m's cancel, so 2/3 of the length. So about 2/3 of the way. So say 1, 2, so about right here. And that seems reasonable. It's been shifted over by the 2m. So my center of mass would be here. So does the center of mass, is that the same thing as the center of gravity? So in most cases, yes. As long as the G acting on this is the same across the entire object, then the center of gravity will be the same. So I don't know, if you're building like something that's going to extend into the atmosphere, maybe they'd be different. I don't know. I can't think of any offhand. So we can refer to them. The center of gravity is where the gravitational force acts. So in this case, let me erase some of this stuff, because let's think about how we could get this thing to be static. So maybe we want to put a pivot somewhere. So we want to put something which will support it. Obviously, we're going to have to put it right here at the center of mass. And the reason for that is that's where the center of gravity is. So this mass over here is producing a force. So we have force mass. So is this one. Force of the 2 mass. And so the distance we just calculated, this was what we're going to do is we're going to calculate the torque. So this would be 2/3 L. And then this one would create 1/3 L. And now we can see the torques. These are in opposite directions because our pivot is here in the center. And what we're doing is we're balancing. Right here you have a normal force up and a force of gravity down. So we're not concerned with this one. So what we want to check is the net torque equal to 0? So the net torque, I said I was going to do an example in another video. I'll do more examples, but the net torque in this case would be the force M times, it's perpendicular, so times 2/3 L. We're checking to see if this is true. And then our other torque is negative. Remember, this direction is positive. So this one is positive, this one is negative. So minus the force of the 2m times 1/3 L. We're saying, is that equal to 0? Now the force of these masses is the force of gravity, so it's mg 2/3 L minus 2mg 1/3 L. And is that equal to 0? So you can see this is going to be 2/3. So we get all of this minus the same quantity, so we get 0 equals 0. So yes, the net torque is 0. This thing is not going to rotate. What about the forces? So all the forces are up and down, and now we have to add in these two. So you also have normal here, and then you have the force of gravity on the entire object. So the net force in the y direction, we're going to check, is that equal to 0? So you have the force over here, which would be mg. That's down. I'm just going to call it down positive. Or here we can do it negative. Minus the mass, the force of everything. So 3m plus m is 4mg. Minus this one, minus 2mg. Plus the normal force equals 0. It's not moving, so we kind of would solve for normal here maybe. I don't know. Anyway, we're not really checking it. You get the idea though. The idea is we just need to check both things, is the net torque and the force of gravity. We'll use both of these for these types of problems. But that's it. That's statics, basic statics. So these conditions, and that's it.